Okay, we're going to pick up with the second day on 9.1, which is on exponential functions. It's really the same material. What I want to do is look at a couple of examples of exponential growth in decay specifically, and how to go through the process of looking at some of the key characteristics of it. So in this example, it says we're going to fold a piece of paper in half. And when we do so, it obviously is going to double in thickness. So if a piece of paper is 0.05 millimeters thick, then you can determine the thickness, which is going to be our y, of a given number of folds, which is x, with the function y equals 0.05 times 2 to the x power. Okay, so again, y is the thickness of the paper, x is the number of times that we've folded it, and this is going to be given to you, but that you should identify as a exponential function. They're asking us to identify the key features of the functions, to graph it, and then identify the relevant domain and range in context of the situation. Okay, so let's first identify the key features. So as you look at this, the equation y equals 0.05 times 2 to the x. In that equation, the base number, the b, is 2. Since 2 is greater than 1, then you know this is exponential growth. And you know roughly what the graph will look like in terms of it's going to increase and increase by that specific ratio, which in this case is we're doubling it each time. Okay. The domain, the beginning for any exponential growth equation, the domain is all real numbers. The range is y is going to be greater than 0, so we know we're going to be above the x-axis. Everything's going to be up there. All right, the y-intercept. We can figure out the y-intercept as usual. The y-intercept occurs when x equals 0. So what is the answer of y when x is 0? So we'll take our exponential growth, put 0 in place of x. Now, 2 to the 0 power. Anything to the 0 power is 1. And then 1 times 0.05 is 0.05, which should make sense, okay? Because at 0, at no folds in the paper, then the paper is 0.05 millimeters thick. So 0.05 is our y-intercept, okay? It's where we cross the y-axis. It's when x is 0. That key features. Second of all, graph it. So when we graph it, we're going to make a chart, a table of values. In this case, I went from -2 to 4. And notice that I take the function and I'm going to replace the x, which is the exponent, with -2. Now be careful when you put all this information into a calculator. 2 to the -2nd, that answer times 0.05 would be 0.0125. Okay. 2 to the -1st, you do 2 to the -1st, then multiply by 0.05, you should get 0.025. Okay. When x equals 0. So 0 folds, remember we just found that. That's the y-intercept. That's at 0.05. So we haven't folded the paper at all. It's at its original thickness. Okay, after one fold, we'll be at 0.1. After 2 folds, we're at 0.2. After 3 folds, we're at 0.4. And after 4 folds, we're at 0.8. Now notice this is not increasing at a constant rate. Double it, double it, double it. So that is a constant ratio. So that's how it becomes exponential growth. That's what you can expect from that. Okay. Now, if we make the graph, we knew exponential growth was going to work like this. This is that curve that represents exponential growth. At -2, we were 0.0125. At -1, we were 0.025. At 0, we were at 0.5. That's the original thickness of the paper. After 1 fold, we're at 0.01. After 2 folds, we're at 0.02. After 3 folds, we're at 0.4, excuse me. And after 4 folds, we're at 0.8. Okay, so we knew the curve was going to look like this. Notice how they scaled the y-axis and so that we could get all this information on the graph. Okay, the label it, the number of folds are our x values. That's our domain. The thickness, that's our y values, that's our range. Okay, so that's what the graph looks like. Generate the equation, or excuse me, generate the table of values, make a sketch. Let me go back for a second. Today you will also be asked to put asymptotes in this solution. The asymptote, remember, is a line that your graph comes very, very close to but never crosses. So in this case, we have a horizontal asymptote at y equals 0. That's the x-axis. We're going to come along this curve. We're going to get really, really, really close to the x-axis, but we're never going to touch it. So this asymptote, and they're going to ask you to put this in your answers today. So you're going to have to label that as an asymptote. Okay. Okay. Next thing, relevant domain and range. Well, we know we got exponential growth here. We knew that by the equation, or the function we were given. Okay. So in general, we know the domain is all real numbers. But how about in our situation? We're saying x could be any number. Well, really, x has got to be a number bigger than 0. There's no such thing as a negative number of folds in paper. Remember, x represents the number of folds. So in context of the situation, the domain is x has got to be greater than 0. Okay, we know in general for an exponential growth function, the y's are always greater than 0, right? They come really, really close to 0, but they never touch. In this case, it's only really our domain is only relevant when we're greater than 0, right? And we know at 0, we're at 0.0 or 0.5, excuse me. That's where the paper begins. At 0, you're at 0.05 thickness. So really, because we're only going to input positive x's, this number is going to start at 0.5, and it's going to get bigger from there. So really the relevant range is from 0.5 and up. Y values are going to be bigger than 0.5 because this is the thickness at 0. So really, I mean, we could say it's bigger than 0, but we can be more specific because we know we're going to begin at 0.5. So that's a little bit about applying other ideas to these rather than just graphing them. Okay, let's look at a decay. This is a very common exponential decay concept, is half-life of a substance. And half-life describes how long it takes a substance to deplete by half. All right, the half-life of caffeine in the body of a healthy adult is approximately 5 hours. So what that means is it takes 5 hours for the body to break down half of that caffeine. So 5 hours to break down half. But for teenagers, it takes longer. Okay. Suppose an energy drink contains 160 milligrams of caffeine. The amount of caffeine wide left in your system after X hours is modeled by this. All right, now this looks kind of complicated, but it really isn't. 160 is the amount you put in to begin with, the amount of caffeine that you take in through an energy drink. A half is our half-life. To cut this substance in half is our base number of 1/2 here. And then this, when X is the number of hours, so in a fifth of an hour, if you put 1 in for X, you're looking at a fifth of an hour. And, 2 hours is 2/5 of our time period to cut the amount of caffeine in half. So that's why it's written like this. You're not going to write these now. They're going to be given to you. But this just looks kind of complex, so I thought I'd show it to you. But this is given. All right, some key features. Well, we know it's exponential decay because our base number here, the exponent x up here, this is the base of that exponential number. That's a half, which is between 0 and 1. So this is decay. So we know it's going to look like this. If you think of your curve, it's going to be it's going to be up here in the negative values for x's and come down as positives and sweep down close to 0. The domain is all real numbers, same as decay, growth and decay. Domain is the same, range is the same. What's the y-intercept? Well, what's the value when x is 0? Should make sense to you here. When x is 0, that means I've done 0. There's no time passed after having taken in that 160 milligrams of caffeine. So 0 out of 5. Well, 0/5 means you got 0. You got no fifths, so that's 0. 1/2 to the 0 power is 1. Anything to the 0 power is 1. So 1 times 160 is 160. Should make sense that at time 0, so you've taken in this drink. Okay, right after I've taken in the drink, I've got all the caffeine in my system, 160 milligrams of caffeine. So 0, 160 is our intercept on the y-axis. Okay, graphing it, same kind of deal. We got to create our model, create our table. And I'm going to start in the -1 and go up to 5. Okay, so I put -1 in place of the x, so that's -1/5. So you got to be careful now. Use grouping symbols. So 1/2 raised to the -1/5 power, and then multiply that by 160, and we'd be at 184. Now that hopefully you understand that that's negative time, which really doesn't exist. But if I have 160 at 0, if I back it up an hour, that meant I had to have more than that in my system prior to. But that really, isn't relevant. We could calculate it mathematically, but it doesn't make sense in terms of the problem. 0, we calculated this. 0/5 is 0. 1/2 to the 0 is 1 times 160 is 160. Okay, now we're going to have to, for 1, that's 1/2 to the 1/5. So we'll carefully generate that in our calculator. Multiply by 160, we're at 139. At 2 hours, that's 2/5 of the time it takes to cut it in half. Okay, we'll be at 121. At 3 hours, we'll be at 106. At 4 hours, we'll have 92 milligrams of caffeine in our system. And at 5 hours, which is 5/5, that's 1. So that's that's the half-life. In 5 hours we should have cut this in half. We are at 80 milligrams. Okay, so that's calculator. Be very careful with it. Generate your outputs. Okay, now graphing it. At 0 we're at 160. Remember, at -1 I said we were 184. In let's see, 1 hour, notice this is scaled by 4, so in 1 hour we're up here at 139. At 2 hours, about halfway between 0 and 4, we are up here at 121, and then we're at 106, 92, and then at 5 hours we've cut the amount of caffeine in our system in half. So in 5 hours we're at 80 milligrams. Okay, what's the asymptote? The asymptote is the number that you approach but never get to, so the asymptote is still y equals 0. Okay, last thing, let's talk about relevant domain and range. This is the same question. So again, we know this is exponential decay. We knew that because the base is a number between 0 and 1. The beginning domain is all real numbers, but in our case, again, it doesn't make any sense to let time be negative. So we're going to let our domain be x values greater than or equal to 0. 0 is our beginning amount of caffeine, so we can use equal to here. The domain, the range, which are our answers, y values, we know they're going to be greater than 0. Okay, because the amount of caffeine is never going to be negative. So we're going to come down and get really, really close to 0 grams of caffeine in our system, but we're never going to get to 0. Okay, if you continually take half of something, you never really get to 0. Okay, so that's looking at those models and how we can do that. Now, today's homework is very similar to last night's in that you're going to have to make tables of values, make graphs, take your time, calculate things carefully. You got unlimited tries at the homework, so use that to help yourself identify and get everything correct. You're also going to be asked to put asymptotes in tonight's homework, so take a good look at that. And generally, we're approaching 0 for an asymptote. Okay, good luck. Get that homework